Welcome, this is Edexcel's M1 June 2015 paper. Now this is the last question, this is question 8, and it's a bit of a tricky one to understand. However, it's quite a tricky topic, but if you understand this topic, then this question is really easy. So either you got this or you didn't. Generally people didn't get half marks of the people I know anyway. I'm just going off how the other people I know did. So, because weirdly enough, I know a few people. Okay, so the first question, part A. So we're given this scenario where we've got an inclined plane and we've got these two are just, I'm going to call them particles. I think they call them objects, but whatever, it doesn't matter. Just two weights. We're told the mass of P on the slope. Obviously, sorry, this slope has got a coefficient of friction, so it's a bit rough. It's not as smooth as I've drawn it, but anyway. So we're told the mass of P is 4 kilograms. The mass of Q, obviously it's smaller, 0.5 kilograms. Obviously the acceleration due to gravity hasn't changed. You call that 9.8 in mechanics. The tan of the angle, so this is this angle I've coloured in green, that is 4/3. Tan of that angle is 4/3. Obviously you would tan invert it to get the angle, but we'll come to that in a second. And the coefficient of friction, normally denoted by this mu symbol, is 0.5, and I've just kind of circled over it, so you can't see it, but hopefully you got it. Okay, as I said, then all this information is given in your exam. Okay, so the part A asks us to find the tension in the rope. Just get the wording right. Tension in the string during the motion. So it's held at rest on a fixed plane. So it's just being, basically, first thing we need to draw on here is all the forces that we've got acting on this particle, on these particles. The easiest one to do is to start with Q. Now, obviously, its weight acts downwards, and we've got mg. Its weight is equal to mgw, and I've got a force upwards. Otherwise, the particle Q would hit the bottom, and we're told it doesn't. So there must be some kind of force holding it upwards, and that's the tension in the rope. Okay. Now that same tension acts down towards P as well. Right. So that's the tension there. The tension is the same throughout. Okay. So that's the particle Q. Now the forces acting at P are slightly different because it's on the inclined plane, and also this inclined plane, as we said, has got friction. Obviously, there is a coefficient of friction in air, but it's not moving, so there's no coefficient that we have to consider for Q. Otherwise, although if we were being really pedantic and we were taking this to university level, then we probably would be considering some kind of forces here. But at AS level, we are not considering that. Or A level, or whatever you're doing this at. Now, the weight that, say this is the centre of the Earth here. Well, obviously, it won't be that close, but you get the idea. The centre of the Earth is not perpendicular to the slope. Now, the weight acts down towards the centre, so it acts straight down. It doesn't care that this is on the slope, it just acts down towards the Earth, so that's mg. Now, the way that acts perpendicular to the slope is mg cos theta. As I said, I explained that in the M1 video. So go on the playlist if you don't get why we've done that. So that's mg cos theta, or cos A. I might refer to it as theta, but I mean A, okay? They mean exactly the same thing. Now, that same force must be acting upwards. We call that the reaction force, or R. Personally, I like to denote it by the letter N, but it would help for other parts of the equation to call it R. Because even though these forces were unbalanced, then we'd have the P that was sinking into the plane, and that just wouldn't make any sense. Unless someone was punching it, but that's a different story. R, so that R is also equal to mg cos theta, because this, or cos A, sorry. Okay, and the force acting down the slope, so down this way, is mg sine theta. As I said, I explained how we come up with all these forces in a different video, so I'm just hoping you understand how we come to these. I don't want to make this video several hours long, otherwise it probably will be, but I don't want to waste too much of your life. And it's mg sine theta, okay? or sine A. Now if you want to draw this on another free force diagram, you're more than welcome to. But I'm just keeping it one diagram for simplicity. Even though it probably makes it a little bit more complicated doing it this way. Now, acting up, obviously we've got the tension pulling it up, because if there was no force pulling it up the slope, then it just rolled down it, like that, just flung off there. So we've got to get the tension acting up. Now, as we had here, where the tension goes all the way down to P, then the tension goes all the way up to Q from P. So we've still got an arrow this way. So we actually look, we've got two opposite tensions, even though they're the same tension. But it's showing it's spread across the whole system. But we've also got, because we've got a coefficient of friction, we're told that, obviously we're going to have to include that somewhere. And that's in the opposite direction to motion. And now, because it's not moving, we're assuming it's been moving downhill. So therefore, it's the opposite direction of motion, so it's up the hill. And we call this UR, or mu-R, sorry. And that is the force which is considered the coefficient of friction. Okay, and that R there is this equation up here. Now I could have called that N and just wrote that F equals UN. It wouldn't matter, just as long as you get that equation in there somewhere. I do apologise, I was going to just leave it, but I do think this pen is probably going to run out at some point. So anyway, leave it actually. Okay, so how does this all help us to work out T? Well, the only thing we can really do, because we can't just say, okay, well, we can come up with an equation that will give us T straight away, just one equation. Well, it's not. We know this is in equilibrium, so both particles are in equilibrium. Now, we have to use both particles, and I'll explain why in a minute. Now, the first one that I expect most of you may have started with is Q. Okay, so what I'm going to be using, the equation that I'm going to be using throughout this whole video is F equals ma, or Newton's second law of motion. Now for P, obviously that equation is going to be modelled slightly in terms of inclined planes, but for Q, that's pretty much what we're going to use. Okay, remember this F is resultant force, it's not a single force. Now the only two forces that we have that are acting on at Q is the weight, which we said was mg, and the tension bringing it up. Now it necessarily doesn't matter which way round you put it. Sorry, just had to plug in my laptop, decided to almost die. So anyway, as I said, we're going to start with Q. Now it sort of does and sort of doesn't matter which way round you do. Either you do mg take t, or t take mg. However, for the way I'm going to do t take mg because which you mean t is starting to get bigger. So I just put t take mg equals ma. Okay, so that's the resultant force at Q. Now, we don't know what T is, we know what the M is because we've got 0.5 kilograms. Now, obviously, G is 9.81, sorry, 9.8. And the mass again is 0.5 kilograms, and we don't know A. Okay. Alright, so that's the first equation. I'm going to call that equation 1. Because that is considering the particle at Q. Now we need to consider the particle at P. So particle, so if I can spell particle, particle P. Okay, so particle P. Now we don't need to include, we don't need to say, okay, well R mg cos, R is equal to mg cos A, because we know that, and that is equal to mg cos A. That's stupid. There's no point putting that down. That was just so you can see I'm not ignoring the vertical forces there, parallel to the perpendicular to the plane. Sorry, but we do need to consider the horizontal forces. Now, the only force that's pulling it down the slope is mg sine theta, or mg sine A. Now, we need to take the difference between mg, the forces pulling it down and the forces pulling it up must be 0, or they must cancel out. So the forces pulling it up, we said tension, and this other force the coefficient of friction times the normal reaction force, so F equals UR. So it's U or mu times R. Now R is mg cos A. I'm just going to put mg cos A in. And we add to that the tension. And that is equal to the mass times acceleration. Now just expand this out in terms of putting it like this. So mg sine A. I've not put the individual values in just yet, so you can get the basic idea of where we're going with this. Take mu times mg cos A. And when you do, you take away a positive, that obviously leaves you with a negative. So it's mg sine A, take u, mu, mg cos A, take t, and that's equal to the mass times the acceleration. So now we sub in what we know. However, before we start to do that, we need to know what A is. Now we didn't for the first, for working out what Q was, and that's because we didn't have to consider any angles. But we're told, it's rather crude in terms of, they haven't just given us the angle. I think it's quite a little bit nasty in that respect. So we know tan A is 4/3. So therefore, we tan inverse both sides, or arc tan. So A is equal to tan inverse of 4/3. So therefore, we get a value for A, and we're told A is equal to 0.93. Okay, now it's actually 0.927, and it goes on. But I've just rounded it for simplicity to 0.93, and I do sincerely hope that is correct, but I'm just going to double check now. Well, you can have a go at this as well, double checking, because I don't want to go ahead with this and they'd be all incorrect. So the tan inverse of 4/3. I mean, it is technically either that or 53.1 degrees, but it's totally up to you. Personally, I would leave it in radians because tan of something is 4/3, so quite a low number, so therefore I'd consider that to be in radians. Okay, so it's 0.927 or 0.93. And then just sub that value for A. As I said, you could have done that in degrees, but generally you'd leave it in radians unless it tells you otherwise. So mg sine, we know the mass, so we're considering P now, so the mass is 4 kilograms, so it's 4 kilograms times 9.8 times the sine of the angle, which is 0.93. Put square brackets around that, just so we can see where we're going with this. Take away the coefficient of friction, so that's 0.5 times mg cos A, so that's 0.5 times 4 kilograms times 9.8 times the cos of the angle, which is 0.93, and we're taking that, so we take T, and that's equal to 4 kilograms times A. Okay, so if we simplify this down, I'm not going to do it individually, you can just do that on your calculator. It's just a case of working out what 4 kilograms times 9.8 times sine of 0.93 is, and 0.5 kilograms times 4 times 9.8 times cos of 0.93, and working out what that is. And if you were to do that and simplify it down, you would get 19.6 newtons, take away T, is equal to 4 kilograms times A. And we're going to call that equation 2. Okay, so we've got equation 1 and equation 2 there. And what you could do now is you could rearrange it, so you could work out, you could take them both away, get a value for A, and then work out what T is from that, or you could simply rearrange this to get T and sub it in to equation 1. So that would help you again work out what T or A is. But as I said, you know, it's totally up to you which way you do it. But you should get a value for T, which is equal to 6.53 newtons. Yeah. The reason I'm doing that as well, first of all, is because I'm quite lazy. But I don't want to take up too much board space, and I can hope you can see it's just equation 1 take away equation 2, so you cancel the T's, get a value for A, and sub it into one of your equations, and then you could work out what T is from that. but I'm assuming that that's okay because that's quite basic maths, and it would take up quite a little bit of the board. And I, can't be bothered doing one of my. Give me a minute where I pause the video and rub half of it off in, well, not a minute. Anyway, waffling. So, key to put that somewhere quite noticeable on your page. T is 6.53 newtons, and also key to remember that all these T's are 6.53s. It's the same all over the whole pulley. And it's also key to mention, I mean, I think this is quite logical because you never get a question, especially in M1, that requires you to work out the friction of some kind of pulley. So we always, in M1, assume this to be a frictionless pulley. So you don't need to consider any resistance forces on the pulley. The only resistance forces you need to consider are the ones that it tells you about, so the coefficient of friction on the plane. Okay, so we've got a value for T, and that is what is asked us to get for part A. So part A is nicely done now. Okay, so part B, the wording of this question I thought was probably one of the harder bits of it. Now it says, find the magnitude of the resultant force of the tension. I think that's essentially what it says on the string, on the pulley. That's essentially what I said was correct. Okay, so what I'm going to do is draw a little, basically all we're really considering is just, you can kind of take out this particle and this particle, and we're just going to focus on, because we know what T is now. The whole point of these two particles being there was to enable us to work out what T is. So for simplicity you can just sort of ignore them, because we're looking at the two resultant forces. So obviously you need to consider the angle still, and I'll explain why in a minute. So you can sort of draw it without the particles on there, but still with the tensions, even though that might not make sense to some people. So we're still going to draw the same sort of system. So we've got an angle, we've got a slope here with an angle A, which we know is 0.93 radians, and we've got a point here of a pulley, and it's got a tension in it, T, and we've got a force that is along the pulley, and we've also called that T. Okay, now these are the two extremes. What this tension is trying to pull it up, and this tension is trying to pull it down. Okay, so the resultant force, naturally you would assume, is going to lie somewhere like this. So it's going to lie, and for on here, just to compare it, it would lie somewhere like this. Okay, so these two diagrams are exactly the same in terms of the every way that they're not. Okay, now just imagine this wasn't a slope, and this was just two forces that were something like this. So you've got, we'll call this T1, T2. This, you don't need to copy this down, this is just to get in your mind how we're going to go and answer this. And you had a resultant force, you generally see that as R, and you might see something like that. So, casting your mind back to, if you've done AS Physics, you would have encountered something like this, and you would have been asked to work out R. And basically what you would have done for that is considered this vertical component, which we call T2, this horizontal component, which we call T1, and use Pythagoras to work out the resultant force in that situation. But obviously we haven't got, the idea is the same. You can see how they compare. Well, these aren't horizontal forces, so we're obviously going to need to calculate the horizontal and vertical components. Okay, but this idea of working out the horizontal and vertical component using Pythagoras to work out what R is. So as I said, we need to look at the horizontal and vertical components. So what we're going to need to do is draw like a little, because this is a vertical component, this T going down, this tension that is going straight down. That is very easy to work out. Okay, and obviously there's no, because this is just vertical, this tension, this one here, or this one, there is no horizontal component of this tension. The only horizontal component of the tension we have is in the string on the other side of the pulley. Now, as I said, the tension is the same throughout, but there's two sort of parts to it. Okay, so there's only one horizontal component on this side, a vertical, sorry, as I said, but on the other side, because it's angled, we've got a horizontal and a vertical component. So we've got two, in essence, we've got two vertical components. So the vertical component of where Q is, and the vertical component of the tension that is attached to P, but we've also got the horizontal component of this tension that is on the side of P. Hopefully that makes sense. So basically, that information should have provided you to draw another sort of triangle on the right hand side. So I'll move away in a minute. Obviously that's 90 degrees. And using alternate angles are equal from GCSE, we should know that's also 9.3 radians. So that's that little angle there between the parallel plane and what I've drawn to be like a little sort of horizontal line. Now, we've got, as I said, we've got a horizontal component here of the tension, so that's T. I'm going to call that T2, and I'm going to call the horizontal component T3. Okay, so what we're going to do is, as I said, split some into horizontal and vertical components. So the first one we're going to do is the easiest. So the vertical components is what I'm going to start with. Okay, so this comes from the T plus, now we work out this T2 by using basic trigonometry. So I've drawn a little right angle here. So we've got a right angle triangle. The hypotenuse has got T. So that's the tension that we know from here is 6.53 newtons. So it's, and we've got an angle here of 0.93 radians. So it's T times the angle times the sine of the angle if you want to work out the vertical component, because you sort of flip it round, imagine it the other way up if you would like, and that would help you to work out the vertical component. As I said, it's just basic trigonometry. So it's T plus T times sine 0.93. Okay, and that's equal to the vertical component. Sorry, my camera's flashing. Is it completely gone? No. So anyway, that's the vertical component. The horizontal components. Okay, they are, now obviously the only horizontal component we've got is this, what I call T3. So it's T, the tension, which is 6.53, times the cos of the angle, cos of 0.93 radians. Okay. Now we know T is 6.53, so you would just sub 6.53 to be T in there, get a value for both of them. It's probably actually a good point to stop. So just be a second while I copy this over. Hello and welcome. This just the other little bit, the video. Now, what we were saying before my camera decided to pack it in was that we have to consider the vertical component and the horizontal component of the tension. Now, obviously in this part, as I said, we've only got the vertical component because it's straight down, so we don't have a horizontal component. However, the other part of the tension, now as I said, the tension throughout is the same. That's a key thing of this question. But this part of the tension, so this section of it, can be split into a horizontal and a vertical component. Now, I've already got a vertical component of this part of the tension, but we've also got a vertical component of the this other part of the tension. So we've got two vertical parts and one horizontal part. Okay, so that's kind of what we've just done there. I've just kind of reiterated that. Now, we worked out what T was. We said T, okay, was 6.53 newtons. Now, it's just a case of subbing in T to the two equations that we've got here. So if you were to do that for the horizontal, it'd be 6.53 times the cos 0.93 radians. And then for the vertical, it'd be T, so it'd be 6.53 newtons, which would be the cube part, 6.53 newtons, plus 6.53 times the sine of 0.93 radians. Okay, and if you were to work them two out, you would get an answers of. So there's one thing actually. So what I'm going to do is work out individual ones for you. So the horizontal component would be 6.53 times the cos of 0.93 or 0.9279 or whatever it rounds to. And that's 3.914, etc. The one above, so that's 6.53 plus 6.53 times the sine of 0.9279, etc. You get 0.729 from here. As I said, in here I've rounded it up to 0.93, but you need to have accuracy. And this gets you 11.75. Now it's just a case of squaring these two numbers and squaring each of the numbers and adding them together and then square rooting the answer. So, as I said, you could just simply work out the horizontal component, work out the vertical component individually, and then add them up, square both of them and add them together and square root, or you could just simply put these two into the square root, square them both and add them together. The same method for both of them. And if you were to do that, sorry, I do apologise. Gee, this is annoying me. 10 inverse 4/3. Sorry, I do apologise. Make sure you calculate in radians, by the way. Well, it doesn't matter. Just need to specify that. Okay, 0.97. Sorry. Okay, so it's a square root of 6.53 plus 6.53 times sine 0.93 or 11.75, whatever. So then you put that in. So plus 6.53 times the sine. So I do apologise. Plus your 6.53 times your cos of 0.927, etc. You square that and you square root it and you get an answer of 12.38. Okay, Newton. So that's your resultant force. It's not exactly very neat, but you get the idea. Can't bother doing it again. I've already done it about 4 times this particular video for certain people over shouting and making me like a complete and utter idiot, which I don't need any help with that. So anyway, thanks for watching. Hopefully it's been of some help. If you want me to have another go at explaining that last question, because I do anticipate it being quite difficult, I'm more than happy to, but I'm assuming that is okay with you. As I said, for the individual forces, so how we got R as mg cos theta, that is in the Mechanics 1 playlist that I've copied over, which is essentially AS Physics playlist, and I've just copied some videos because I'm quite lazy and I couldn't be bothered redoing them again. But anyway, thanks for watching, and we'll see you in the next video.